What makes a planet a planet? At first glance, a planet might seem like a simple glowing sphere orbiting the sun, yet defining what truly makes a planet requires more nuance. Astronomers describe planets as bodies massive enough for their gravity to shape them into round forms, and which orbit a star without clearing a path cluttered with other debris. They are distinct from moons, asteroids, and comets, yet each of these cousins shares hints of the same cosmic origins. A planet's identity comes from balance between gravity and mass, between orbital motion and the pull of neighboring objects. Some spin slowly, some quickly, yet all follow a celestial rhythm that has persisted for eons. Their surfaces may be rocky, icy, or gaseous, but the defining quality is their autonomy. Planets carve their own paths through space, each a unique participant in the solar system's intricate dance. In observing them, we begin to understand how structure emerges from chaos, how order can arise in the infinite expanse of the cosmos, and why these luminous orbs have captured our imagination for millennia. How many planets are in our solar system? Think about this. Our solar system is home to 8 recognized planets, each vastly different from the next, yet all bound in a gravitational embrace around our star. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, names etched into human culture, science, and imagination. Pluto, once counted among them, was reclassified as a dwarf planet, reminding us that the cosmos does not always fit neatly into categories. Beyond these 8, countless smaller bodies, asteroids, comets, and Kuiper belt objects, orbit the Sun, hinting at a solar system far richer and more diverse than our simple planetary count might suggest. The number 8 is not just a statistic. It is a reflection of careful observation, mathematical reasoning, and the evolving understanding of celestial mechanics. Each planet occupies its niche, contributing to the balance and rhythm of the system. Even in their differences, sizes, compositions, atmospheres, a delicate harmony persists, and the question of how many planets exist becomes a meditation on order emerging from cosmic chaos. Why are some planets rocky and others gaseous? Here's something surprising. The composition of planets tells a story about their birth and position. Closer to the Sun, heat drove away volatile elements, leaving rocky, dense worlds like Mercury, Venus, Earth, and Mars. Their surfaces are solid, their landscapes carved by impacts, volcanism, and tectonic forces. Farther out, beyond the frost line, the colder temperatures allowed lighter gases like hydrogen and helium to accumulate, forming massive giants: Jupiter, Saturn, Uranus, and Neptune. These gaseous planets are not solid in the way Earth is. Their cores may be rocky, but layers of swirling gas dominate. This contrast creates a poetic symmetry. Near the warmth of the Sun, small, tangible worlds. In the icy reaches of space, giants of swirling clouds and winds. By observing composition, we trace the history of the solar system itself, seeing how temperature, distance, and gravity sculpted each planet's identity, shaping the diversity that now fills our celestial neighborhood with wonder. How does the Sun control the planets? Let us go back in time, to the beginning of the solar system. The Sun, a luminous ball of plasma, dominates its domain, with gravity so immense that it orchestrates the motion of every planet, asteroid, and comet. Each orbit is a silent negotiation between centrifugal force and gravitational pull, a balance that has persisted for billions of years. The Sun's light and energy shape planetary atmospheres, drive climate, and even influence magnetic fields. Solar winds sweep across the system, carving paths and eroding surfaces, yet always maintaining the cosmic rhythm. Without the Sun, planets would drift aimlessly into the void. With it, each world follows a measured, predictable path. This gravitational choreography teaches us about power, balance, and subtlety. How a single star can dominate yet allow individuality. How energy radiates and structures emerge. And how life, as fragile as it is on Earth, owes its existence to a star's constant, unwavering presence. Why is Mercury so extreme? At first glance, Mercury seems almost impossibly harsh, a world of contrasts and extremes. It hugs the Sun closer than any other planet, basking in temperatures that can soar above 430 degrees Celsius during the day. Yet at night, Without an atmosphere to trap heat, it plunges to minus 180 degrees. These staggering swings are a result of its thin exosphere, a near vacuum that cannot distribute warmth, leaving one side blistering and the other frozen. Mercury's surface is scarred with craters, evidence of countless impacts over billions of years, each collision leaving its mark on this small, dense planet. And yet, despite its harshness, Mercury has a subtle rhythm, a 3-2 spin-orbit resonance, rotating 3 times on its axis for every 2 orbits around the Sun. This intricate balance, etched into the planet's motion, reflects the delicate interplay of gravity and motion, a cosmic choreography that persists across eons. Mercury may be extreme, but in its extremity, it teaches us about the resilience and precision of celestial mechanics. Could Mercury have ice on its surface? Here's something surprising. Even on a world scorched by the sun, ice can exist. Mercury's polar regions contain deep craters permanently shielded from sunlight. Temperatures in these shadowed hollows remain cold enough to preserve water ice for billions of years. Radar observations from Earth first hinted at these icy deposits, and later missions like MESSENGER confirmed them. The ice is likely mixed with dark, carbon-rich material, creating an almost spectral contrast against the gray regolith. This discovery transforms our perception of Mercury, revealing a hidden duality, a planet both scorching and frozen, violent and serene. It reminds us that even in extreme conditions, delicate pockets of stability can persist. The presence of ice on Mercury is a quiet testament to the complexity of planetary surfaces, to the subtle ways in which the cosmos balances heat, shadow, and time, and to the enduring mysteries that await exploration in the smallest corners of our solar system. How long is a day on Mercury? Mercury's days are strangely long by Earth standards. One full rotation on its axis takes 58.6 Earth days, while it completes an orbit around the Sun in just 88 Earth days. This unusual relationship means that a single solar day, from one sunrise to the next, lasts 176 Earth days. Imagine the sun rising, climbing slowly, and then dipping below the horizon months later, painting the surface in prolonged shadows and endless heat. Such a rhythm creates extreme thermal cycles, yet it also produces a mesmerizing pattern of light and darkness across craters and plains. This slow spin, combined with Mercury's orbital eccentricity, gives rise to peculiar phenomena, such as the sun appearing to briefly reverse direction in the sky from certain vantage points. A day on Mercury is not simply measured in hours, but in the unfolding of light over months, a reminder of how time itself can stretch and bend in the vastness of space. Why is Venus called Earth's twin? Venus is often called Earth's twin, a reflection of our planet in many ways, yet distorted and dangerous. Similar in size, mass, and composition, Venus has a rocky surface and a thick atmosphere. From afar, it shines with a brilliant, almost serene light, masking its true nature beneath clouds of sulfuric acid and layers of carbon dioxide. Its atmosphere traps heat in an intense greenhouse effect, driving surface temperatures hotter than Mercury's, despite being farther from the Sun. This resemblance and divergence make Venus a cautionary tale, a mirror showing what could happen if atmospheric balance is disrupted. Venus reminds us of the delicate equilibrium that allows Earth to host life. Its twin-like appearance sparks both wonder and reflection, illustrating that similarity does not guarantee familiarity, and that beauty can conceal danger in the cosmic dance of planets. Could humans survive on Venus? Let's imagine for a moment trying to stand on Venus. The experience is immediately impossible with current technology. Its crushing surface pressure is over 90 times that of Earth, like being deep beneath the ocean. The atmosphere is suffused with corrosive clouds of sulfuric acid, while the temperature exceeds 460 degrees Celsius, hot enough to melt lead. Even robotic explorers last only hours under these conditions. Survival would require unimaginable protective suits, habitats impervious to heat, pressure, and toxic gases. Yet, in the clouds above the surface, at altitudes of around 50 kilometers, conditions are milder, with pressures and temperatures closer to Earth's. Some scientists envision floating habitats, or drones exploring this temperate layer, studying the planet while suspended in dense acidic skies. Venus challenges our imagination, asking whether life can endure extremes and teaching us that survival in the cosmos demands ingenuity, adaptation, and humility before forces far beyond our natural limits. What secrets lie beneath Venus's clouds? Beneath the thick, yellowish clouds of Venus lies a world of mystery and intensity. Radar mapping has revealed mountains, vast plains, and enormous volcanic structures, some reaching heights comparable to the tallest peaks on Earth. The surface is shrouded in a relentless greenhouse, where molten rock and high pressure conspire to create conditions alien to life as we know it. Volcanoes may still be active, periodically resurfacing regions and releasing gases into the atmosphere. Lava flows carve channels across plains, frozen in place under the oppressive heat. Scientists ponder whether this volcanic activity could have been more moderate in the distant past, perhaps even allowing transient conditions favorable to life. Beneath the clouds, hidden from direct observation, Venus tells a story of fiery renewal and planetary evolution, a planet alive in a way that is invisible yet undeniable. Each radar pulse peering through the haze uncovers contours and valleys, inviting us to imagine a landscape both familiar and utterly alien. What makes Earth so special? Earth's uniqueness is quiet but profound. Its gravity, atmosphere, and distance from the sun create a haven where liquid water can exist, a rare gift in the vast reaches of space. The planet's magnetic field shields life from harmful solar and cosmic radiation, while tectonic activity recycles nutrients, shapes continents, and stabilizes the climate over eons. Earth is not the largest planet, nor the fastest spinning, but its harmony of conditions fosters an astonishing diversity of life. Life itself interacts with the planet, transforming the atmosphere, soils, and oceans in ways that feed back into climate and habitability. Earth's beauty is not only in mountains and seas, but in this interplay of systems, the delicate balance that sustains life while allowing change and evolution. In studying Earth, we learn what makes a planet habitable and why such worlds may be extraordinarily rare, teaching us reverence for the fragile oasis on which we live. How does Earth protect life? Think about the invisible shields surrounding Earth. Our magnetic field deflects charged particles from the sun, preventing them from stripping away the atmosphere and protecting living organisms from harmful radiation. The atmosphere itself filters ultraviolet light, moderates temperatures, and maintains pressure suitable for life. Clouds and oceans distribute heat, while the ozone layer absorbs radiation that would otherwise scorch the surface. Even the moon contributes indirectly, stabilizing Earth's axial tilt, and thus seasonal variation, maintaining climatic balance over millennia. These protections are not passive. They are active interactions between core, atmosphere, and celestial companions. Earth is a living system, resilient yet fragile, its defenses orchestrated over billions of years. Understanding these safeguards deepens our appreciation of life's persistence and illuminates what may be required to sustain or terraform worlds elsewhere. Why is water essential for life? Water is the silent architect of life. It dissolves nutrients, enables chemical reactions, transports materials, and regulates temperature. On Earth, oceans, rivers, and clouds are not just scenic, they are active participants in climate, geology, and biology. Water shapes the landscape, carves valleys, and forms the rhythm of weather. Its unique properties allow it to exist in solid, liquid, and gaseous states within a habitable range, creating a dynamic environment where life can flourish. Without water, molecules cannot assemble into complex structures, cells cannot function, and ecosystems cannot persist. In planetary exploration, the search for water is synonymous with the search for life. Even traces of ice or vapor on distant worlds spark questions about potential habitability. Water is more than a substance, it is a bridge between chemistry and life, a medium through which the universe becomes aware of itself. Why is Mars red? Mars glows with a rusty hue, captivating the human eye for centuries. Its red color comes from iron oxide or rust, covering the surface. Billions of years ago, Mars may have had flowing water, interacting with iron-rich rocks to oxidize minerals and create the red dust that now blankets plains and craters. Windstorms lift and distribute this dust, ensuring the planet retains its signature color. The red surface is more than an aesthetic detail. It reflects Mars's history of chemical reactions, climate shifts, and planetary evolution. Observing Mars's red glow prompts reflection on how seemingly simple elements can reveal complex stories of ancient rivers, vanished atmospheres, and the slow interplay of wind and rock. Mars's crimson tone is a reminder that color in the cosmos is a message, a clue to past processes and hidden secrets waiting to be uncovered. Could Mars support life? At first glance, Mars seems a barren, dusty world, yet its surface whispers of possibilities. Ancient riverbeds, deltas, and mineral deposits suggest that water once flowed freely, carving channels and nourishing a landscape that may have been hospitable to microbial life. Today, conditions are harsher. The atmosphere is thin, cold, and composed mostly of carbon dioxide, offering little protection from solar radiation. Still, beneath the surface, pockets of ice, and perhaps briny liquid water, might persist, creating niches where life could survive. Extremophiles on Earth, organisms thriving in deserts, frozen lakes, and acidic springs, hint that life could endure on Mars in hidden refuges. Robotic explorers and orbiters continue to search for chemical signatures and organic molecules, clues to whether Mars ever hosted life, or might again in the future. The red planet, silent and distant, reminds us that habitability is not always obvious, and that life, if it exists there, may be subtle, resilient, and waiting quietly beneath the surface. Are there rivers on Mars? Imagine walking along the bed of an ancient Martian river, dry for billions of years, yet still carved into the rock. These channels wind across the landscape, evidence of flowing water that shaped valleys, transported sediments, and eroded rock. Some rivers branched like terrestrial deltas, suggesting long periods of flow, perhaps supported by rain or melted ice. Others appear as single channels, possibly formed by sudden floods or catastrophic events. Observations from orbiting spacecraft reveal minerals like clays and sulfates, formed only in the presence of water, confirming Mars's wetter past. These ancient rivers are more than geological features. They are narratives of a dynamic world, a record of climate and potential habitats for life. By tracing their paths, we glimpse the rhythms of Martian seasons, the potential for ancient ecosystems, and the deep story of a planet that once may have shared more with Earth than its red hue suggests. Why does Mars have two moons? Mars is accompanied by two small moons, Phobos and Deimos, tiny, irregularly shaped bodies that orbit close to the planet. Their origin remains a subject of scientific debate. Some theories suggest they are captured asteroids, pulled from the asteroid belt and trapped by Mars's gravity. Others propose they formed from debris ejected during a colossal impact, coalescing into moons over time. Phobos, the larger, orbits so closely that it rises and sets twice in a single Martian day, gradually spiraling inward toward its eventual destruction. Deimos, smaller and more distant, drifts serenely, nearly a celestial whisper against the dark sky. These moons remind us that planetary systems are not static. They are shaped by gravity, collisions, and time. Even tiny companions influence tides, surface activity, and exploration strategies, adding depth to the story of Mars and offering glimpses of its turbulent past. How big is Jupiter really? Jupiter is a giant in every sense, a swirling mass of gas and storms that dwarfs every planet in our solar system. Its diameter stretches over 139,000 kilometers, more than 11 times that of Earth, and its volume could contain more than 1,300 Earths. Despite its immense size, Jupiter rotates rapidly, completing a rotation in just under 10 hours, flattening slightly at its poles and creating a distinct equatorial bulge. Its gravity dominates the outer solar system, influencing asteroid belts, comets, and even the orbits of neighboring planets. Jupiter is more than a planet. It is a guardian, a furnace of hydrogen and helium, a planet whose storms have raged for centuries. The sheer scale of Jupiter humbles the imagination, offering perspective on the variety of planetary forms and the power that gravity wields in shaping worlds. To study Jupiter is to confront the sublime, the overwhelming majesty of a planet both alien and profoundly influential. What is the Great Red Spot? The Great Red Spot is Jupiter's most iconic feature, a swirling storm larger than Earth itself, a tempest that has raged for at least 400 years. Its crimson hue emerges from complex chemical reactions in Jupiter's upper atmosphere, where ammonia, phosphorus, and sulfur compounds mix under intense heat and pressure. The storm rotates counterclockwise, with winds exceeding hundreds of kilometers per hour. yet it has remained remarkably stable, an enduring vortex in a planet of perpetual turbulence. Observing the red spot is like witnessing the heartbeat of Jupiter, a force of nature, timeless and immense. It reveals the dynamics of gas giants, where layers of clouds interact, temperatures vary, and energy is redistributed across vast distances. The Great Red Spot reminds us of the majesty of planetary atmospheres, the scale of storms beyond earthly comprehension, and the elegance of chaos contained within predictable motion. How many moons does Jupiter have? Jupiter's moons are a universe unto themselves, with over 90 confirmed moons. Each orbits in its own rhythm, from tiny, irregular rocks to the enormous Galilean moons, Io, Europa, Ganymede, and Callisto. Ganymede alone is larger than Mercury, and each moon carries its own mysteries, surfaces, and histories. Some are volcanic, some icy, and some potentially harbor oceans beneath frozen crusts. Jupiter's gravity orchestrates their motions with precision, creating resonances that keep their orbits stable over eons. The sheer number and variety of moons illustrate how complex planetary systems can be, even around a single gas giant. Observing these moons is like exploring a miniature solar system, where each body is a unique world with lessons to teach about formation, geology, and the possibility of life in extreme environments. They remind us that planets are rarely solitary, and that their companions may be as fascinating and diverse as the planets themselves. Why are Saturn's rings so famous? At first glance, Saturn's rings seem almost magical, a luminous band encircling the planet in elegant symmetry, composed of billions of particles, ranging from tiny dust grains to massive chunks of ice and rock. The rings reflect sunlight, giving Saturn its signature brilliance. They are remarkably thin, often only tens of meters thick, yet they span hundreds of thousands of kilometers in diameter. Their origin is still debated, perhaps remnants of a shattered moon or primordial debris left over from Saturn's formation. The rings are dynamic, sculpted by gravitational interactions with moons and resonances that create waves, gaps, and spokes within the bands. Observing them reminds us that planetary systems are active, evolving structures, and that beauty in the cosmos often arises from complexity and motion. Saturn's rings are both a scientific treasure and a visual marvel, offering a glimpse into processes that shape not only rings, but entire planetary systems. What are Saturn's rings made of? Saturn's rings are primarily ice, mixed with dust and rocky fragments. These particles range from microscopic grains to massive boulders, each reflecting sunlight and scattering it across the vast expanse of the rings. Collisions between particles, gravitational nudges from moons, and the planet's immense tidal forces keep the rings in constant motion. Observations show intricate structures, spiral waves, gaps, and even temporary ringlets, each telling a story of gravitational dance and orbital resonance. The composition and behavior of the rings provide insight into planetary formation, the evolution of satellites, and the delicate balance that allows such structures to persist. In many ways, Saturn's rings are a laboratory for understanding broader cosmic processes, a frozen symphony of ice and rock, orbiting a planet with grace and precision, silently demonstrating the interplay of physics, time, and gravity. Could you stand on Saturn's moons? Unlike Saturn itself, which is a gas giant without a solid surface, many of its moons offer more tangible terrain. Titan, Saturn's largest moon, has a thick atmosphere and solid ground, with rivers and lakes of liquid methane. Enceladus, though smaller, is icy and dynamic, with geysers venting water into space. Landing on these moons would require ingenuity and preparation, as temperatures are frigid and surfaces treacherous. The gravity is lower than Earth's, making movement easier, but also affecting human physiology. Yet, standing on one of Saturn's moons is not mere imagination. Robotic landers and orbiters have already probed these worlds, mapping surfaces, analyzing atmospheres, and even detecting hints of subsurface oceans. These moons are laboratories in their own right, offering a bridge between exploration and scientific discovery, and inviting us to envision humanity as visitors on distant alien terrains. Why is Uranus tilted sideways? Uranus is a planet unlike any other. Its axis is tilted at approximately 98 degrees, causing it to roll along its orbit like a barrel, rather than spinning upright like most planets. This extreme tilt likely resulted from a colossal collision early in its history, a cataclysmic event that reshaped the planet's rotation and interior. The tilt creates unusual seasons, with poles experiencing decades of continuous sunlight or darkness. Such an orientation challenges our understanding of planetary dynamics and the effects of large impacts. Uranus demonstrates that planets are not static, but vulnerable to dramatic changes, reminding us of the violent processes that sculpt worlds. Observing its peculiar rotation teaches us about energy, momentum, and the fragility of equilibrium in celestial systems, while inviting contemplation of how a single event can redefine an entire planet's character. Could Uranus have seasons like Earth? Think about this. Uranus experiences seasons unlike any other planet in the solar system. Due to its extreme axial tilt of approximately 98 degrees, each pole faces the sun for around 42 Earth years, bathing one hemisphere in continuous sunlight while the other endures decades of darkness. Unlike Earth's rhythmic four seasons, Uranus's seasons are prolonged, stretching across decades and creating patterns of atmospheric circulation and temperature shifts that are subtle yet profound. The planet's faint internal heat and slow rotation contribute to gentle, barely perceptible weather changes, but clouds, haze, and faint storms respond to this unusual sunlight distribution. While human life could not survive on Uranus, these extreme seasonal dynamics teach us how planetary orientation, solar energy, and atmospheric composition interact to shape climates. Observing Uranus's unique dance reminds us that each planet is a world unto itself, where familiar concepts like seasons can be transformed into patterns we can scarcely imagine from our terrestrial perspective. How many moons orbit Uranus? Uranus is accompanied by 27 known moons, each a frozen fragment of the past, orbiting in the quiet vastness of its tilted system. The largest, Titania and Oberon, are icy, heavily cratered worlds, their surfaces etched with fractures and ridges from ancient geological activity. Smaller moons like Miranda display extreme features, cliffs, valleys, and surfaces resembling patchwork terrain, hinting at collisions or internal stress. The moon's orbits are influenced by Uranus's unusual tilt, creating a system unlike any other in the solar system, with interactions and resonances that shape their paths. Studying these moons offers insight into the history and evolution of Uranus itself, revealing clues about impacts, tidal forces, and the migration of icy bodies. Together, they form a miniature planetary system, each orbit a slow, deliberate movement in a cosmic ballet, a reminder of the diversity and intricacy that exists even among the lesser-known planets. Why is Neptune so windy? Neptune is a world of relentless motion, where winds race across its deep blue atmosphere at speeds exceeding 2,000 kilometers per hour, faster than any storm on Earth. These storms form in the outer layers of Neptune's thick atmosphere, where heat from the planet's interior meets the frigid temperatures of space, creating dynamic turbulence. Vast bands of clouds, methane-rich haze, and transient dark spots trace the movement of these winds, shifting and evolving over time. Despite its distance from the sun, Neptune's internal heat fuels this atmospheric fury, demonstrating that energy within a planet can drive climate and weather as profoundly as solar radiation. Observing Neptune reminds us that the solar system is not a static place, it is alive with motion, energy, and transformation. Even in the distant, frozen reaches beyond Saturn, planets possess personalities, moods, and rhythms, invisible yet undeniably present in the restless winds of Neptune. Could you survive Neptune's storms? Imagine standing on a platform above Neptune's clouds, feeling winds stronger than any hurricane, enveloped in frigid temperatures around minus 220 degrees Celsius. Survival would be impossible without extreme protection. The atmosphere is mostly hydrogen and helium, with traces of methane, offering no breathable air. Storms whip at supersonic speeds, forming dark vortices and dynamic cloud patterns that shift unpredictably. Even robotic probes are challenged by such conditions, barely scratching the surface before extreme cold, pressure, and turbulence intervene. Yet, these storms are not just destructive, they are magnificent demonstrations of fluid dynamics on a planetary scale, a visual symphony of motion and energy. Observing Neptune's storms teaches us about the limits of exploration, the diversity of planetary atmospheres, and the raw power that exists in worlds beyond our own. It is a reminder that the cosmos contains both beauty and danger, often intertwined in ways we can only begin to comprehend. How many moons does Neptune have? Neptune hosts 14 known moons, each unique in size, orbit, and character. Triton, the largest, is geologically active, with geysers of nitrogen venting from its icy surface, and an orbit that suggests it was once a captured object from the Kuiper belt. The smaller moons are irregular, likely captured asteroids or fragments from past collisions, orbiting in a chaotic dance that contrasts with Neptune's distant serenity. These moons are more than companions, they are archives of Neptune's history, preserving evidence of formation, capture, and migration. Triton's retrograde orbit, moving opposite Neptune's rotation, hints at violent events in the past, while the tiny inner moons help maintain the planet's faint ring system. Together, Neptune's moons are a microcosm of celestial evolution, revealing the interconnectedness of gravity, motion, and time, and providing both mystery and guidance for future exploration beyond the frozen edges of our solar system. Why was Pluto demoted? Let's go back to 2006, a moment that stirred both scientific debate and public sentiment. Pluto, once cherished as the ninth planet, was reclassified as a dwarf planet by the International Astronomical Union. This decision arose from a clearer understanding of what defines a planet. A celestial body must orbit the Sun, be spherical due to its own gravity, and have cleared its orbital neighborhood of other debris. Pluto met the first two criteria, but shares its orbit with numerous Kuiper Belt objects, meaning it has not cleared its path. Far from being a demotion in importance, this reclassification refined our understanding of the solar system, revealing a vast population of small, icy worlds beyond Neptune. Pluto's status change reminds us that science evolves with evidence and observation, and that our definitions must adapt to the complexity and diversity of the cosmos. Pluto is still a world of intrigue, with unique geology, atmosphere, and moons, proving that significance is not diminished by categorization. Could Pluto have ice volcanoes? Beneath Pluto's distant, frozen exterior lies evidence of geological activity, including features resembling ice volcanoes or cryovolcanoes. These structures likely erupt a mixture of water, nitrogen, methane, or ammonia, flowing across the surface in slow, viscous streams that freeze into smooth plains. Observations from the New Horizons mission revealed large domes with depressions at their summits, suggesting past eruptions of volatile ices. While these processes are slower and colder than volcanism on Earth, they indicate that Pluto's interior retains heat and dynamic energy, challenging the notion of this dwarf planet as inert. Ice volcanoes are more than curiosities. They testify to the subtle, yet persistent forces that shape distant worlds and hint at the complex interplay of temperature, pressure, and chemistry that sustains planetary activity even on the edge of the solar system. What is Pluto's atmosphere like? Pluto's atmosphere is tenuous, composed mainly of nitrogen, with traces of methane and carbon monoxide. It expands as Pluto approaches the Sun in its elliptical orbit and contracts as the planet retreats into colder distances. This thin, shifting envelope forms hazes and layers visible from spacecraft and Earth-based telescopes, creating a delicate, ethereal shroud over the icy surface. Despite its thinness, the atmosphere interacts with the surface, transporting volatile ices and sculpting features over geological timescales. Sublimation of surface ice into gas drives winds and redistributes material across plains and mountains. Pluto's atmosphere is fragile and transient, a whisper of air in the distant cold, yet it illustrates how even a small remote world can exhibit dynamic processes. Studying it helps us understand atmospheres beyond Earth and the mechanisms that sustain or dissipate them in extreme environments. Are there planets beyond our solar system? Beyond Neptune and Pluto lies an almost infinite expanse of possibilities. For decades, astronomers have confirmed thousands of exoplanets orbiting stars far beyond our Sun. These worlds vary wildly. Some are scorching hot giants hugging their stars, while others are rocky super-Earths, some in the habitable zone where liquid water might exist. Methods like the transit technique and radial velocity allow us to detect these distant worlds, revealing a universe teeming with planets. Observing them teaches us about planetary formation, migration, and diversity, showing that our solar system is but one example among billions. The existence of planets beyond our own reminds us of the vastness of space and the endless potential for discovery, prompting reflection on our place in the cosmos and the possibility that life may exist elsewhere, waiting to be found. What are hot Jupiters? Hot Jupiters are gas giants, orbiting extremely close to their parent stars, sometimes completing an orbit in mere days. These worlds defy our early expectations, showing that planetary systems can take unexpected forms. Their proximity to intense stellar radiation inflates their atmospheres, creating searing temperatures and complex weather patterns. Some experience atmospheric evaporation, leaving trails of gas stretching into space. Hot Jupiters illustrate the dynamic and sometimes violent nature of planetary migration, where gravitational interactions nudge giants inward from the cold outer reaches. Studying these worlds deepens our understanding of how planets form, evolve, and interact with their stars, and challenges assumptions about what is typical in a planetary system. They are a striking reminder that the universe is full of surprises, where extremes can be as instructive as the familiar. Could super-Earths be habitable? Super-Earths are planets larger than Earth but smaller than Neptune, and they capture the imagination of astronomers searching for life beyond our solar system. Their increased mass can hold thicker atmospheres, which may help regulate temperature and protect the surface from radiation. If they reside in the habitable zone, the region around a star where liquid water could exist, these planets could potentially host oceans, weather systems, and maybe even life. Yet their size may also lead to extreme volcanic activity or crushing surface pressures, conditions hostile to Earth-like life. Observing super-Earths is like peering into alternative possibilities for planetary evolution, worlds similar yet fundamentally different from our own. They challenge us to expand our understanding of habitability, asking what forms of life might exist under conditions unlike anything on Earth, and reminding us that the cosmos is filled with possibilities, some inviting, some terrifying, and all profoundly instructive. What are rogue planets? Rogue planets drift alone through the galaxy, untethered to any star, wandering in perpetual darkness. Without the warmth of a sun, their surfaces are frozen and dark, yet internal heat from residual formation or radioactive decay may sustain subsurface oceans in some cases. These lonely travelers challenge our conventional notions of planets, showing that planetary systems are dynamic and sometimes violent, capable of ejecting bodies into interstellar space. Rogue planets are difficult to detect, their faint presence betrayed only by gravitational effects or occasional infrared signatures. Yet they hold secrets about the formation and evolution of planetary systems, and hint at worlds that experience life differently, if at all, in solitude and shadow. The existence of rogue planets is a reminder that the universe is not uniform, that even a planet can be an orphan, carrying its own story across the dark stretches between stars. How do planets form? Planet formation is a slow poetic process spanning millions of years. It begins in a protoplanetary disk of gas and dust. Surrounding a newborn star, tiny particles collide, stick together, and gradually build larger bodies, known as planetesimals. Gravity begins to dominate, pulling these planetesimals together into protoplanets, clearing paths in the disk, and shaping the architecture of the emerging planetary system. Rocky planets like Earth form closer to the star, where lighter gases are blown away, while gas giants form further out, where ices and gas are abundant. This process is influenced by turbulence, collisions, and migration, leading to diverse planetary systems with a wide array of sizes, compositions, and orbital arrangements. Studying planet formation allows us to see the origins of our own world, revealing how the interplay of gravity, material, and time sculpts the cosmos into the intricate planetary systems we observe today. How are asteroids different from planets? Asteroids are remnants of planetary formation, small, irregularly shaped bodies that never coalesced into full-fledged planets. Unlike planets, they lack sufficient gravity to become spherical and cannot clear their orbits of other debris, composed of rock, metal, or ice. Asteroids serve as time capsules, preserving the chemical and physical conditions of the early solar system. They exist in belts, such as the main asteroid belt between Mars and Jupiter, or as isolated wanderers crossing planetary paths. Studying asteroids informs us about the building blocks of planets, the history of collisions and migrations, and even the delivery of water and organic material to Earth. While diminutive compared to planets, asteroids are crucial witnesses to cosmic history, tiny storytellers of a time when the solar system was young, chaotic, and brimming with potential. What role do comets play in planetary systems? Comets are icy voyagers, traveling from the distant reaches of planetary systems toward the inner regions. Their composition of ice, dust, and frozen gases preserves primordial material from the birth of their systems. As they approach a star, the ice sublimates, forming glowing tails that stretch millions of kilometers, a visual reminder of their transient beauty. Comets can deliver water, organic compounds, and other materials to planets, potentially seeding them with the ingredients for life. They also act as probes of the outer regions of planetary systems, carrying chemical fingerprints of their formation environment. Each comet is a messenger from the edge of the solar system, a relic of its earliest moments, and a participant in the ongoing cycle of matter and energy. Observing comets allows us to glimpse the origins and evolution of planets, reminding us that even small bodies play vital roles in cosmic ecosystems. How do planets get magnetic fields? Planets generate magnetic fields through the movement of electrically conducting fluids in their interiors, a process known as the dynamo effect. On Earth, molten iron in the outer core circulates, creating a protective magnetic shield that deflects harmful solar and cosmic radiation. Gas giants like Jupiter and Saturn have metallic hydrogen layers that churn similarly, producing enormous fields that extend far into space. Even smaller bodies, like Mercury, retain weak magnetic fields, hinting at a partially molten core. Magnetic fields are more than protective barriers. They influence atmospheric retention, auroras, and the trajectories of charged particles in space. Understanding planetary magnetism reveals not only the internal composition and dynamics of worlds, but also their potential for habitability. Magnetic fields are invisible guardians, sculpting interactions between planets, moons, and the stellar wind, silently shaping the conditions under which life might arise. Which planet is the hottest? At first glance, one might think Venus is the hottest planet due to its proximity to the Sun, but it is the greenhouse effect that seals its fate. Thick clouds of carbon dioxide and sulfuric acid trap heat relentlessly, raising surface temperatures to around 465 degrees Celsius, hotter than Mercury despite being further from the Sun. Venus's atmosphere circulates energy efficiently, creating super-rotating winds and a planet-wide furnace. Its extreme heat prevents liquid water, transforms rocks into molten or baked surfaces, and challenges any notion of habitability. This scorching world demonstrates how atmospheric composition can dominate climate and how proximity to a star does not alone determine a planet's temperature. Venus is a cautionary tale, a mirror reflecting the delicate balance required for planetary habitability, and a stark example of how runaway greenhouse effects can create a world unrecognizable to our familiar, life-friendly Earth. Why do planets have seasons? Seasons are born from the tilt of a planet's axis, combined with its orbit around the Sun. Earth's 23.5-degree tilt creates the familiar cycle of spring, summer, autumn, and winter, as sunlight strikes different hemispheres more directly over the course of a year. Mars experiences similar effects, though with greater variation due to its eccentric orbit. Uranus, with its extreme tilt, has seasons lasting decades, while planets like Jupiter and Neptune show subtle seasonal changes influenced by tilt and internal heat. Seasons are not merely aesthetic, they affect climate, weather patterns, and even biological cycles on planets with life. They are the gentle reminders that celestial geometry governs the rhythms of worlds, and that the interplay of tilt, orbit, and sunlight produces cycles that shape the character and habitability of planets. Observing seasons elsewhere expands our understanding of how energy and motion create temporal patterns in the cosmos. Do other planets have rings like Saturn? Saturn's rings are iconic, but it is not alone. Jupiter, Uranus, and Neptune all possess ring systems, though less pronounced and harder to see. These rings are composed of dust, ice, and small rock fragments formed from collisions, captured material, or remnants of moons. While Saturn's rings gleam brightly, those of Uranus and Neptune are faint and narrow, and Jupiter's are thin and mostly dark. The presence of rings demonstrates that planetary systems are active, with ongoing processes of collision, erosion, and gravitational sculpting. Rings are dynamic laboratories, showing how moons and particles interact and providing insight into the evolution of planetary systems. They remind us that beauty in the cosmos often emerges from structure and motion, and that even subtle features can tell profound stories about the forces shaping planets and their companions over millions of years. How do moons affect their planets? Moons exert influence far beyond mere companionship. Earth's moon stabilizes our axial tilt, moderating climate and creating tides that have shaped coastlines and influenced ecosystems. Jupiter's large moons interact gravitationally, producing tidal heating that fuels volcanic activity on Io or maintains subsurface oceans on Europa. Saturn's moons, sculpt rings, generate gaps, and contribute to orbital resonances that maintain system stability. Even small distant moons can trigger complex gravitational interactions, subtly altering planetary rotation or orbital patterns over millions of years. Moons are partners in planetary evolution, their presence shaping geology, atmospheres, and potential habitability. They demonstrate that planets are not isolated. They exist in a web of relationships where gravity and motion weave patterns that persist across cosmic time, silently influencing the story of their host planets. Can planetary atmospheres escape into space? At first glance, a planet's atmosphere seems permanent, a protective blanket enveloping the surface. Yet, over time, gases can escape into space, shaped by gravity, solar radiation, and magnetic shielding. Smaller planets with weak gravity, like Mars, gradually lose lighter molecules, thinning their air and altering climate. Stellar winds can strip particles away, while high-energy ultraviolet light breaks molecular bonds, enabling escape. Even Earth loses some hydrogen to space, though our magnetic field and replenishing processes preserve a stable environment. Atmospheric escape is not mere loss. It is part of a planet's evolving story, influencing climate, surface conditions, and habitability. By studying this process, scientists learn why some worlds remain vibrant and life-friendly, while others wither quietly, teaching us that a planet's atmosphere is a living, dynamic system, delicately balanced between retention and loss. Could planets exist around binary stars? Binary star systems, where two stars orbit each other, create complex gravitational environments. Yet planets can and do exist within them. Some planets orbit both stars in a wide circumbinary path, like Tatooine in fiction, experiencing alternating light and warmth from each star. Others orbit one star closely, with the companion star exerting tidal and gravitational influences that shape climate and orbit. These planets challenge our understanding of stability, habitability, and orbital mechanics. Observations show that planet formation is resilient, capable of persisting even in seemingly chaotic systems. Studying planets in binary systems expands our concept of possible worlds, revealing that life-supporting conditions might arise in arrangements far different from the comforting regularity of our Sun and Earth. The universe allows surprises, demonstrating adaptability and creativity in the architecture of planetary systems. How do rogue planets drift through space? Rogue planets are nomads, wandering the galaxy without a sun to call home. Their journeys are shaped by violent ejections from nascent planetary systems or gravitational interactions with other stars. These lonely planets travel through interstellar space in perpetual darkness, perhaps retaining heat from formation or internal radioactive decay. Some may carry subsurface oceans beneath thick ice, isolated habitats shielded from the cold void. Their existence shows that planets are not always bound, highlighting the dynamic, sometimes chaotic nature of stellar neighborhoods. Detecting rogue planets is challenging, relying on gravitational lensing or infrared emissions, yet each discovery offers insight into the diversity and resilience of planetary formation. Rogue planets are a testament to the unpredictable poetry of the cosmos, solitary worlds tracing silent paths across the galactic night. What makes a planet habitable? Habitability is a delicate balance, an interplay of factors that allow life to arise and persist. Temperature, atmospheric composition, availability of liquid water, and energy sources all shape the potential for life. A planet's distance from its star defines a habitable zone. Yet internal heat, magnetic fields, and geological activity also play crucial roles. Too close, and the planet may overheat. Too far, and water freezes. Atmospheres must protect from harmful radiation while allowing chemical cycles essential for life. Even moons can contribute, stabilizing rotation or generating tidal forces that drive oceans and geological activity. Habitability is not a single trait, but a symphony of conditions working together. In studying habitable worlds, we glimpse not just possibilities elsewhere, but the remarkable circumstances that make Earth a nurturing home and the subtle vulnerabilities that make life a precious, rare phenomenon. Which planets will we explore next? Our curiosity propels us forward, from robotic explorers to ambitious human missions. Mars remains a priority, with rovers, orbiters, and sample return missions, unveiling its geology, climate history, and potential for past life. Beyond, the icy moons of Jupiter and Saturn, like Europa and Enceladus, attract attention for their hidden oceans and promise of habitable niches. Proposals for Venus's atmosphere, Titan's lakes, and even asteroid mining hint at the expanding frontier of exploration. Future missions will combine robotic precision with eventual human presence, pushing boundaries of distance, technology, and imagination. Each new world we visit enriches our understanding of planetary formation, the potential for life, and the diversity of conditions across the cosmos. Exploration is both scientific and philosophical, a journey of discovery and reflection, inviting humanity to reach beyond familiar horizons and touch the universe in profound, tangible ways. What surprises await us in the planetary frontier? As we look outward, the planetary frontier stretches beyond what our eyes can see, and our instruments can yet fully measure. Each new discovery challenges our assumptions. Worlds orbiting two suns, planets with scorching temperatures or frozen oceans, rogue planets adrift in darkness, and moons concealing oceans beneath icy crusts. These surprises remind us that the universe is far more diverse and imaginative than our early models could predict. As technology advances, from space telescopes to interplanetary probes, we begin to map these hidden corners, uncover chemical signatures, and detect atmospheres that hint at potential life. Future exploration may reveal phenomena we cannot yet imagine, reshaping our understanding of what a planet can be. The planetary frontier is not a boundary, but an invitation, a call to curiosity, patience, and wonder. Each discovery enriches our story, offering glimpses of how complex, dynamic, and extraordinary the cosmos truly is. And perhaps, somewhere among these distant worlds, answers await that will illuminate not just the universe around us, but the very nature of life itself.